Hello everyone, welcome to today's video lecture. In the last video lectures, we covered what are the different number systems present and how to convert from decimal to other base and other base to decimal. In the last video lecture, we were solving this problem which is binary to other base. So, in the last lecture, we considered how to convert binary to other base. In the conversion process, we understood that sometimes we can directly convert to the other base, sometimes it is not possible. When it is possible, when it is not possible. In order to understand that, the required base has to be written in terms of two powers. So here A can be written as 2 power 3, 16 can be written as 2 power 4, 4 can be written as 2 square. It means that a binary to octal, hexa and base 4 is directly possible. And if you ask, can you convert binary to base 5 directly? Then the answer is no. Because we cannot write 5 in terms of 2 powers. As we can't write 5 in terms of 2 powers, it is not possible directly from binary to base 5. It doesn't mean that we cannot solve the problem. We can solve the problem, but it is not directly possible. We have to take the help of decimal. By using the decimal, we can convert into base 5. First we do conversion from binary to decimal, then decimal to base. That's the thing. But here our interest is binary to other base direct conversions. So we understood that how to convert binary to octal. I start the video, the last lecture. At this moment, I just given these three as a task. Okay, let us complete that now. Okay, now 10001.01 and it's a binary number and we need to convert it to 60. As I said earlier, 60 can be written as 2 power 4. Now this power we are going to take as a 10. So we take the number 10001.01. Now we make a group of 4 bits. From there I have to start the grouping. So if this kind of a question arises, if there exists a fractional point, it's also called as reference point. Draw a line at the fractional point. From the fractional point towards left and towards right. Towards left count 4. 1, 2, 3, 4. Draw line in A. Now here, I just count only 1. There are 3 bits missing. Then, you can always add as many zeros as you want at the left hand side. Now there are 4 here. Now here when I count, there are only 2. This is 0, 1. Here also we add 2 zeros. Now, in each group, there are 4 bits. Now, represent each group in its hexa equivalent. So, 0001 is a 1, 0001 is a 1, and 0100 is a 4. Therefore, it is 11.4 and it is base 6. Okay? Right. So, we got the answer which is 11.4 and base 6. Okay. Now, we consider how to convert it to base 4. Right. Now, the base 4 as 4 is what? 2 square. Now, we take the help of power. The power is 2. We make group of 2 bits. Okay. We draw a line here. After drawing a line, we count 2. 1, 2. I do now. Again count 1, 2, and 2. Now count 2. As there is only single bit, I add 1 thing. Now in each group, there are 2 bits. So after grouping that, represent each group in its base 4 equivalent. Now 0, 1 is a 1, 0, 0 is a 0, 0, 1 is a 1, and 0, 1 is a 1, and there is a fractional point here. And we got the answer in this. So the answer is 1, 0, 1.1. Right, we learned how to convert binary to other bits. Now, if the question is binary to base 5, I again say this, as 5 we cannot write in terms of a 2 power, we cannot directly convert in this fashion. What we have to do is, we have to take the help of decimal, that is 1,000,000, 1.01. Base 2, first convert into decimal. Okay, and we know that the decimal equivalent is 17.25. If at all you wanted to understand why it is 17.25, you can check back the previous video lecture. In that lecture, we solved this one, binary to decimal, and we got the answer 17.25. And even in the previous lecture, we converted the 17.25 to the other base, that is base 5. And we got the answer is 32.1 bar. Okay, so to understand this problem, you can cross check the previous video. Okay, right. But remember, here what we are understanding is binary to other base straight approach. It means without taking the help of decimal. How one can convert to the other base. If the base is written in terms of 2 powers, we can directly convert. If you cannot write the base in terms of 2 powers, we cannot directly convert. We have to take the help of decimal, that is binary to decimal, then decimal to other base. Here the other base is 5. Okay, right. Next, we consider other base to binary. How to convert other base to binary? We consider the same previous problems, which is 21.2 and it is base 8, 11.4 base 16, 32.1 recurrence base 5, 101.1 base 4 need to be converted into binary. We'll see how to solve this problem. Okay, so binary to other base to binary. These are some other bases, and we are trying to convert that into base. Here, the procedure is, we take the octal number 21.2. Sometimes it is directly possible, sometimes it is not. Again, when it is possible, if we can write the base in terms of a 2 power, we can directly convert. So here 8. What is 8 here? 8 is 2. Then the procedure is represent each digit. Represent each digit in 3-bit binary equivalent form. Okay. So what I have to do is, as 8 is 2 power 3, I have to represent each digit in 3-bit. Each digit must be in 3-bit binary equivalent format. Now, I'll take 21.2. Before I do this problem, what is the meaning of 3-bit equivalent format? For example, if you take 1 can be represented in many ways. In fact, infinite ways you can represent the 1. Now, 1 can be simply represented as a 1 can be represented as a 0, 1 can be represented as a 0, 0, 1, and even the 1 can be represented as 3 zeros and 1. Among these 4 representations, we will take 3-bit representation. 3-bit representation means, if we count the number of bits present, that must be 3. In the third representation, 1, 2, 3, there are 3 bits. So, we consider the 3-bit representation of 0, 0, 1 for 1. Now, each digit has to be represented in 3 bits. Therefore, 2 is 0, 1, 0. And 1 is 0, 0, 1. And again this 2 is 0, 1, 0. And a fraction point here. And we got the answer binary. And we can ignore the 0, which is the leftmost part, and for the fraction part, rightmost part can be ignored. So the answer is 1,000,1.01. So we got this 1,000,1.0. Okay. So this is how we convert octal to binary. Represent each digit in 3-bit binary equivalent format. Next, we consider hexadecimal 11.4, and it's a base 16. Now here the base is 16. So what is 16 here? 16 is 2 power 4. As 16 is 2 power 4, represent each digit in how many bits? We have to represent each digit in how many bits? 4 bits. Okay, because it's a 2 power 4, we take the help of our. We have to represent each digit in 4-bit binary equivalent format. Here again there are 4 representations. Among these 4 representations, we consider the last one, which is 0,0,0,1. We'll solve the problem now. It's a 11.4. Okay, and it's a base 16. Each digit has to be represented in 4 bits. So 1 is 0,0,0,1. Again, this 1 is 0,0,0,1. And this 4 is 0, 1, 0, 0. And let the fraction point here. And it is binary. You can ignore these 3 zeros and zeros, and you get 1, 0, 0, 1.01. So again, this is 1, 2. So like this. Right. Next one, if you consider the base 5, we cannot solve directly because 5 we cannot write in terms of 2 powers. Now, we'll take a fourth one. 101.1 base 4. Okay. Now here 4 is what? 2 square. So as 4 is 2 square, represent each digit in how many bits? 2 bits. Binary equivalent format. Therefore, among these 4 representations, which one I consider? One is 0, 1. Right. So by using that help, we'll solve this problem now. Okay. And it's a 101.1 and it's a base 4. Represent each digit in 2 bits. So it's a 0, 1, 0, 0, and 0, 1, and it's again 0, 1. The correct one here. And we can ignore 0. It's 1, 0, 1, 0, 1. But like this we can convert. Now coming to this third problem, how to do this? As we cannot write 5, okay, as we cannot write 5 in terms of 2 powers, the approach is always the same, which I said earlier. First 32.1 recurrence and it is base 5. Okay, as you cannot write 5 in terms of 2 power, it is not possible to write. Okay, what we have to do is, we have to take the help of decimal. It means first of all it has to be converted into decimal. Then from decimal to byte. So how to convert other base to decimal? This we covered in the first lecture. You can check that one. So we got the answer is 17.25. Again, how to convert decimal to binary? Again, this was covered in the video lecture 1. You can check that if you want. Here the answer is 1.01. And you get the base. This is the only way one can convert the other ways which you cannot represent in terms of a 2 power into byte. Okay? Right. So here the answer is again 1.01. So here we understood how to convert other ways to binary to other ways, when it is directly possible, when we have to take the help of decimal. Okay? Sometimes we have to take the help of decimal, sometimes we can directly convert. When we can directly convert, if the given base can be written as 2 powers, we can directly convert. If we cannot write the given base in terms of a 2 power, we have to take the help of decimal. Next one, we consider octal to hexadecimal. Okay, how to convert octal to hexa? So this is octal 21.2 and we are asked to convert into hexadecimal. This is the question. Conversion from octal to hexa. Here, remember a point. We cannot directly convert octal to hexa. We have to take some help. The help you can take either from decimal or binary. It means we have to convert octal to decimal first, after that decimal to hexadecimal. Or you can convert octal to binary, then binary to hexadecimal. Whatever the procedure you feel easy, we can take. My opinion is octal to binary, then binary to hexadecimal, because it is very simple and straightforward. Let us understand why it is simple. Suppose I am doing 21.2, which is an octal. First I am converting to binary. The conversion of binary I just explained. Okay, right. Each digit must be how many bits? It must be how many bits? 8 is 2 cube, therefore 3 bits. 0, 1, 0, 0, 0, 1, 0, 1, 0 and a fraction point. And it's a binary. Now you want hexa. Now what we have to do is group into 4 from the fractional point. Okay, right? 0, 1, 0, 0, 0, 1, 0, 1, 0. From the fractional point towards left, count 4. There are no add 2 zeros. That is 3. Add 1. Represent each digit in hexa. 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 The fraction. And we got hexa. So it's 11. Okay, I just taken the intermediate step is binary. And one can solve the problem by using the decimal help also. If you want to use the decimal help, the procedure is 21.2 base 8. First has to be converted into decimal. It means here 8 over 0, 8 over 1, 8 over minus 1. We have to write the powers. First, base powers on the top of the given number. 8 2s are 16 plus 1 plus 2 by 8. When you add all those, you will be ending with the 17.25 base 10. The problem is not over. Now the 17.25 has to be converted into hexa. The procedure is integer part has to be divided with the required base 191. 0 times 1, answer is 1 1. That's the integer part answer. 0.25 need to be multiplied with 16, which is 4.00. 4, next multiplication is 0.00 into 16, which is 0.00, stop it. So the fractional part answer is 4. So the overall answer will be 11.4. There is 16. So whatever the approach we follow, we end with the same answer, which is 11.4. Either you take the help of binary or you take the help of decimal. The end result is same. But you try to understand the headache in the procedure of decimal and the easiness in the procedure of binary. The binary is always very easy and convenient method to convert octal to hexa. Why? Because it's just representing each digit in binary equivalent, then it is grouping and writing hexa. But here there is so much math involved. You have to do the multiplications, you have to do the divisions, again multiplications. There is a huge procedure involved with the help is decimal. Okay, so my suggestion is always whenever you are converting octal to hexa or hexa to octal, take the help of binary. Okay. If it's the hexadecimal to octal, we do the same. First hexadecimal is converted into binary, then binary to octal. Now we consider some problems. Find the decimal equivalent of 116. This is a question. It's a IAS question, which was a previous year IAS question. Find the decimal equivalent of 116, and they have given 4 options for this. Okay, so find the decimal equivalent of 116. They have given 4 options: 260, 250, 194, and 9. Okay, we can pause the video for a second and you can try on your own, then check the result. Okay. So the question is, find the binary equivalent of 116. Now, there is a tendency that one can consider the base of the given digits as 60, because we have seen 4 number systems which are binary, decimal, octal and hexadecimal, and we do find this letter C in hexadecimal. So there is a chance that one can consider 116 as hexadecimal and solve the problem. Now, as you consider this as a hexadecimal, what we do is hexadecimal to decimal. We write 16 powers. 16 power 0, 16 power 1, 16 square. So 16 square plus 16 plus C. A is 10, B is 11, C is 12, so it is 12. So how much? So 56, 22, 256, 276. 284. Okay, so we get 284 and it is this. Now, the answer is 284. And when we check the answer list, option list here, it says the option is not here, right? Okay. It does mean that can we take option none because 284 is not here? Yes, there is a chance. Yeah. We can take none if you consider this as 60.